Curvilinear coordinate systems 20, the magnetic field inside an infinitely long solenoid is uniform, it's P0 QZ hat. Determine the vector potential A such that curl A is equal to B. For this situation, the magnetic field can also be derived from a scalar potential B is equal to minus gradient phi. Why is this the case and what is phi? And the magnetic field inside a straight wire aligned with the z-axis and carrying a uniformly distributed current can be expressed using cylindrical coordinates as b0 rho over rho 0 in q phi hat direction, where b0 and rho 0 are constants. In this case, the magnetic field can still be obtained from a vector potential, B is equal to curl A. Find this vector potential A. Now, however, it is no longer possible to find a scalar potential such that B is equal to minus gradient phi. Why is this the case? So when we looked at the divergence and curl of the magnetic field, the first magnetic field given for infinitely long solenoid, we found that they're both equal to 0. Therefore, B can be written as curl A or minus gradient of phi, as we have shown using Einstein's subscript summation notation, and we've obtained a vector potential A, B0 rho over 2 is E phi hat, using Stokes' theorem for this loop. Now, I want to check this result, first of all, using cylindrical coordinates. So if I remember the position vector r written in cylindrical coordinates, this is equal to rho cosine phi, the polar angle, ex hat, the azimuthal angle phi, plus rho sine phi ey hat, plus z in ez hat direction. And let's recall the scale factors. H sub rho is the magnitude of the partial derivative of r with respect to rho. And if I do that, what would I get? The partial derivative would get rid of these two rows. I would get square root of sine square plus cosine square, which is equal to 1. And if I look at the scale factor for phi, h sub phi is the partial derivative of position vector r with respect to the azimuthal angle phi. And this magnitude is going to be, now in row parentheses, I would have minus sine phi and plus cosine phi, which would give me square root of sine square plus cosine square. So I would get a rho here for the scale factor. And h sub z is simply equal to 1. Now, if I look at curl A, B is supposed to be equal to curl A. So let's perform this curl using the cylindrical coordinates. It is 1 over the product of the scale factors. So it's going to be equal to 1 over rho times 1 times 1. The determinant h rho e rho hat, which is e rho hat, h phi e phi hat, which is rho e phi hat, and hc ez hat, which is ez hat. And then I have partial derivative with respect to rho, partial derivative with respect to phi, and partial derivative with respect to z. Then I have h rho a rho, which will give me just a rho. Then I have h phi a phi, which will give me rho a phi, and hc az will give me az. So we have to perform this determinant. Okay, and that's equal to, now if I substitute for A here, I only have a phi component. So I will have 1 over rho again. This determinant E rho hat del rho, and A rho is 0 because A was in E phi hat direction. A rho is 0. Then I have H phi, which is rho E phi hat, del phi, A phi. Now what is the phi component of A? B0 rho over 2. And that has to be multiplied with rho. So I'm going to get B0 rho squared over 2. And then I have EZ hat del z, and AZ is simply equal to 0. So we have to take this determinant. Now let's take a look at the determinant with respect to the first row here. For E rho hat part, I would get del phi of 0, which is 0, and then z derivative of B0 rho squared over 2, that would also give me 0. So I would get no contribution from the rho component. So I have 1 over rho. The first term is 0. The second term, I cross out the first row and second column. Del rho of 0 is 0. Del z of 0 is 0. So I would get another 0. And as for the last term, EZ hat, I have rho derivative of B0 rho squared over 2. That would give me 2 rho over 2. So that's just B0 rho. So this would give me 2 B0 rho over 2 in EZ hat direction. And when I look at it, you can see that I will have the 2's cancelling and the rho's cancelling. I will get magnetic field is equal to B0 EZ hat. And that's exactly what we have for the magnetic field, B0 EZ hat. So this calculation shows me that our result for the vector potential A seems to be correct. Now, we had also shown that curl of this magnetic field is equal to 0, which means it can be derived from a scalar potential. B is equal to minus gradient phi. So if I write minus gradient phi using the cylindrical coordinate system, I have minus gradient of phi. This is equal to minus the partial derivative of phi with respect to rho in E rho hat direction, because the scale factor H rho is equal to 1. Then I have minus 1 over H phi, which is rho, 1 over rho, partial derivative of the scalar function phi with respect to the azimuthal angle phi, E rho hat. And then I have partial derivative of minus the partial derivative of phi with respect to z EZ hat, because the scale factor H sub z is equal to 1. And this is supposed to be equal to B0 EZ hat. Okay. And so all of these terms, rho derivative and phi derivative, should be 0. But z derivative is B0, which means I could write the scalar function phi up to a constant as minus B0 z. So I could add an arbitrary constant there if I wish, because the rho and phi derivatives would be 0 and z derivative would be 0, so that would have no contribution. So I can take this constant to be 0 and say that this is my scalar potential function, and that can be used to produce this magnetic field. Now, looking at the second part of the problem, I'm looking at the magnetic field due to a wire, a uniform wire. This can be written as B0 rho divided by rho 0 in E phi hat direction. And I was told that it cannot be written as a minus gradient phi. In order to show that, I have to look at curl of this magnetic field, curl B. 1 over the product of the scale factors is 1 over rho for the cylindrical coordinates. And now I have h rho e rho hat, h phi is rho e phi hat, and hz is 1, so ez hat. Del rho, del phi, del z. Now I need h rho b rho. B rho is 0 because magnetic field is in E phi hat direction, so this first term is 0. H phi is rho, so B0 rho squared over rho 0 is what I would get here. B0 rho squared over rho 0, and Hz is 0, Bz is 0, so that doesn't contribute. So this determinant is what I need. Now, looking at the first term, E rho hat term, phi derivative of 0 is 0, z derivative of this is 0, so no contribution from E rho hat. For the second term, rho derivative of 0 is 0, z derivative of 0 is 0, no contribution from E phi hat. There would be a contribution from Ez hat, which is due to del rho, so I would have 1 over rho. The derivative gives me 2b0 rho over rho 0. So for this one, del rho of this minus 0. So this would give me Ez hat. And the rho's would cancel here, and I'm getting a non-zero answer. This is non-zero. Therefore, the magnetic field cannot be written as minus gradient of a scalar function because curl of a gradient is 0. All right. So we find this result. On the other hand, if I look at divergence of the magnetic field, divergence of B, this is 1 over the product of the scale factors, which is 1 over rho. Then I have partial derivative of h phi hz, which is rho b rho with respect to rho. Then I have partial derivative h rho hz, which are 1, p phi derivative with respect to phi. Then I have partial derivative h rho h phi is rho, so h rho is 1 with respect to z. So this is what I have to perform. Okay, So first of all, B row is 0. So therefore, I'm going to get a 0 for this one. And BZ is 0, so I'm going to get a 0 for this one. And when I look at B phi, which is B0 row over row 0, there is no phi dependence. Therefore, I'm going to also get a 0 from this one. So divergence of B is indeed equal to 0. Because divergence of a curl is equal to 0, B can be written as curl of a vector potential A. Curl of A. And we can find that vector potential. So if I write down curl of A, let's open up some space here. Okay, now I'm going to write curl of A using cylindrical coordinates. It is 1 over the product of the scale factor, so it's 1 over rho, determinant E rho hat del rho A rho, and H phi, which is rho, so rho E phi hat del phi and rho A phi. And then I have EZ hat del Z AZ. This determinant now there's only a phi component in the magnetic field. Therefore, I should only consider this term, the phi term. Del rho of AZ minus del Z of A rho. So this is going to give me 1 over rho del AZ del rho of rho A del rho of AZ crossing out this term del AZ del rho minus del Z of A rho, but there is a minus sign in the determinant, so let's just do the second one first. Del AZ del rho which one is the second one? Del Z of A rho. So del A rho del Z minus del rho of AZ. So that's what we have. And this is to be multiplied by rho E phi hat. So I've already operated the minus sign by switching the places of these two terms. And this must be equal to B0 rho over rho 0 in E phi hat direction. I see that these two rows will cancel out, and I have del A rho del Z minus del AZ del rho equals B0 rho over rho 0. So the answer is not unique here, so I can try setting a rho is equal to 0, in that case I would get partial derivative of AZ with respect to rho is B0 rho over rho 0. So that means I would have to integrate this, the minus sign B0 rho squared over 2 rho 0. So that would be equal to AZ. All right. And that would satisfy this equation. I can also set a phi is equal to 0 for simplicity, and I only have this z component remaining here. So this would give me one possible answer for the vector potential A minus B0 rho square divided by 2 rho 0 in EZ hat direction. This is a vector potential A that satisfies this equation. Now, if you look at the z part of this equation, so let's be careful here about this part. Del phi of AZ is already equal to 0. Del z of rho A phi, I want it to be equal to 0 because I don't want an E rho hat component. So that's why I can set A phi to 0. And that would give me the rho component of magnetic field, B rho, to be 0. So this would guarantee that. On the other hand, if I look at the z component, if I look at the phi component, del rho of AZ, so that phi component is this equation, and z component, del rho of rho A phi, when A phi is 0, this is 0. Del phi of A rho is 0 because I have set A rho to 0, and that would give me no z component. So this would also guarantee that BZ is equal to 0. So I have checked that my choice for A phi being 0 and A rho being 0 work, giving me no rho or z components for the magnetic field, but there is only a z component of the vector potential, which gives me a phi component, a non-zero phi component for the magnetic field. And that vector potential is minus B0 rho square over 2 rho 0 in EZ hat direction. Okay, now in this part, first of all, I wanted to check my vector potential A that I obtained in the previous video, and I took the curl of that vector A using cylindrical coordinates 1 over h rho h phi hz, which is 1 over rho, h rho e rho hat, h phi e phi hat, h c e z hat, del rho, del phi, del z, a rho, which is h rho a rho, rho a phi, which is h phi a phi, and az, which is h c a z. So this determinant indeed gives me B0 EZ hat that corresponds to this magnetic field. Then I was told that this new magnetic field, and also I've determined the scalar potential function that refers to it. B is equal to minus gradient of phi. So writing the gradient in cylindrical coordinates, minus 1 over h rho del phi del rho e rho hat, minus 1 over h phi e phi hat, minus 1 over h c del phi del z e z hat. That gives me the scalar potential up to a constant is what I can use. Now, when this magnetic field is used, its curl I have shown to be not equal to 0, which means it cannot be written as minus gradient of a scalar function, but its divergence is 0. Therefore, it can be derived from a vector potential A, and if B is equal to curl A, then I can do this general curl for the cylindrical coordinates, and I'm basically free to set a rho to 0 and a phi to 0. I only need an AZ component here. Why? Because I'm going to get del del rho of AZ minus del del Z of A rho with a minus sign, that they switch places. And this is the phi hat component, so I could choose a rho to be 0. In that case, AZ turns out to be minus B0 integral of this rho squared over 2 rho 0. One of these rho's disappeared. And then I have checked my result. If I set a rho to 0 and a phi to 0, I indeed obtain B rho and BZ to be 0, but B phi is reproduced with this choice of the vector potential A.